My screen is visible.
Yeah, yes, sir, it's visible.
Okay, so let me grab the question first. We will discuss the concept. This is the question. So this is problem 5.38 of Sonntag 6th edition. So what does the problem say? We have ammonia at 0 degrees Celsius, 60% quality. It is contained in a rigid 200-liter tank. The tank and ammonia is now heated to a final pressure of 1 megapascal. So we have to determine the heat transfer for the process. Okay, so let us draw a tank, and inside this tank we will write down state 1, it is 0 degrees Celsius and x equal to 0.6. Additionally, it is given that this volume is 200 liter. State 2, it is given that the pressure is 1 megapascal and nothing else. So effectively we have to determine the heat transfer in the process. So it's a let's draw the control volume first. We will draw the control mass. This is the control mass. All of the ammonia inside is the control mass. Let me just draw ammonia as this. Okay, all the blue thing is the control mass. Don't be confused by the dotted line not going all the way, but it does. So the next thing we will do is draw the schematic, and this is before even you sort of open EES or the tables or whatever. So let us draw a tentative schematic of how the process will look like. So on the PV diagram, we have the initial condition is 0 degrees Celsius. So let us draw the isotherm which corresponds to 0 degrees Celsius. Let us say that this is the isotherm which corresponds to T equal to 0 degrees Celsius. And because the quality is 0.6, we can then presume that the point lies somewhere over here. Okay. Now it is given that the ammonia is heated up until it reaches 1 megapascal pressure. So let us say that this is the horizontal line which represents the pressure of 1 megapascal. And because it's a closed volume, the thing that will remain constant across states 1 and 2 will be the specific volume. So the specific volume is constant. Because of that, the process will look like a vertical line and it will go upwards. Now, as of now, we do not know whether point 2 lies in the superheated zone or does it lie on the saturation curve, saturated vapor curve, or whether it lies inside. That is not important for us to know right now. All we need to know is state 2 will be qualified by a state so that V2 will be equal to V1. Are we in a position to know what V1 is? And the answer is yes. We precisely know what the quality is at state 1. So the strategy would be as follows. We will write down the first law for the control mass, wherein we have Q12 minus W, let me just use our old notation. U2 minus U1 is equal to Q12 minus W12. Now the question arises whether we have some work done. Is there some work done in the system? Anyone?
No.
So there is no work done because the boundaries are all rigid. This cancels out. Or not cancels out, rather it is identically equal to 0. So we have U2 minus U1 is equal to Q12, and that is the heat transfer that we must determine. And this will be equal to mass times the specific volume at state, specific energy at state 2 minus the specific internal energy at state 1. And mass we can easily find out. How can we easily find out the mass? Because we know what the specific volume at state 1 will be, and we know that this volume has a total of 200 liter. So the mass is equal to the volume over the specific volume. Using this, we can easily evaluate what the mass will be. So we have our task laid out. So let me just zoom out a bit. Let me open EES first. We will do it quickly using EES, and then we will see how the problem can be done using a table. That is not very much difficult because by now you at least know how to look up the table. And I've told this time and again, it's not a question of whether you use a table or EES or whatever it is. It's just a matter of first understanding what the schematic is and then applying that information to just fetch properties from EES, as we will see. So let me unshare my let me share this entire screen now. So the entire screen should be visible to you now, right?
Yes, sir.
So now we'll go to preferences. We'll increase the font size because otherwise in the recording it will not pop up. So we have the initial temperature as 0 degrees. So we will write T1 equal to 0. We will write X1 is 0.6. And first of all, we will fetch what? The volume. So V at 1 will be volume ammonia T equal to T1, X equal to X1. Let us run this. So we have specific volume as 0.1741. So let me just note it over here. This is how I would have done it as a student who only has EES as a property fetcher. So I get V1 is equal to 0.1741 meter cube per kg. Okay, so using this, I should immediately find out the total mass. So mass will be equal to total volume, that is 0.2 meter cube, because 200 liter is 0.2 meter cube divided by the specific volume, which is 0.1741 meter cube per kg. And so what is this? So using my calculator, I can easily find
1.148.
correct. So 0.141, 1.148. So I'll just approximate it as 1.15 kg. So I have found out what U is. Now what is the second step? I must find out what U1 is. Okay, I can easily find that out. So U1 will simply be int energy ammonia T equal to T1, X equal to X1. Let us see what the value is. 882.5 kilojoule per kg. Having this information, let us see what state 2 will be. So state 2, we have that the specific volume at 2 is going to be specific volume at 1, which is equal to 0.1741 meter cube per kg, and we know that P2 is 1 megapascal. So we precisely know what the two endpoints are. Now I can write down P2 is equal to 1000 because we must input it in kilopascal, and we will write down V2. Let me just do it the old way, like you don't know anything about EES, you just want to fetch properties. I'll simply write V2 0.1741. All right. So with the help of this, what do we need to find? Obviously, we need to fetch what the internal energy at state 2 is. Let me run this, and I should have the value of the internal energy at point 2, which is 1510 kilojoule per kg. So using this, I have U2 equal to 1510 kilojoule per kg. So finally, I'm able to find out the total heat transfer, which is mass, that is 1.148 times 1510 minus 882.5. And using my trusty old calculator, this comes out to be 1.148. 1510 minus 882.5. 720.37 kilojoule. 720.37 kilojoule. Okay, this is how you have to approach the problem. Is that fine? Any doubt? The answer given in the book is 720.75 kilojoule. I think we are pretty close. So let's take a step back and say that you also want to know how to do it using a table. Well, it's quite simple because the first the first state is directly given in the saturated dome. So the first thing you will do, I will just tell you the strategy and I request you to look it up in the actual table. So the strategy. First thing, because you know that everything is in the saturated dome, it immediately makes life easy. It immediately makes life easy. So first step, you go to saturated ammonia table. So because X is given, you can find out V1 as V of the fluid plus 0.6 times VFG. Okay. And similarly, you will also be in a position to find out the internal energy, specific internal energy using UF plus 0.6 times UFG. Okay, this much should be clear to everyone. Now, why did you calculate V1? Because that comes as the input to the V2. So step 2, you know what V2 is, and the pressure is 1 megapascal. So what should you do? In the saturated ammonia table, and I will just go there in a moment, you will first see. So this strategy should be clear in everyone's mind without even having to open the table. In the saturated ammonia data, you will look up 1 megapascal and you will see whether V2 is less than V of the vapor or V2 is larger than V of the vapor. What does the first point mean? What does this mean? And what does this mean? If V2 is less than Vg,
Inside the dome.
it would mean you have to still look into the saturated ammonia table, right? That is correct. If this is true, you would then look up which table?
Superheated vapor.
You would then look up superheated ammonia. That is precisely correct. So let us do that. Let me open up Sonntag. Sonntag tables. I'll simply open Sonntag tables. Let me know if the screen is visible. So we're in saturated water. This is water pressure. So this is all water. This is all water. Okay, this is ammonia. So are you able to see this?
Yes, sir.
So let us look at ammonia. So we are looking at table B.2.1. The pressure is close to 1000 kilopascal. Okay. And over here, what do you see? You see that the vapor specific volume is 0.12813. Over here, you are able to see that at approximately 1000 kilopascal, this is 0.12813, whereas we had obtained 0.1741. So what does that mean? We should then look up superheated and ammonia tables, right? This should be clear to everyone. There should be no doubt in this. So let us go to superheated ammonia, and inside superheated ammonia, we will look up the 1000 kilopascal data. This is the 1000 kilopascal data for superheated ammonia. Let me take a screenshot of this. Let me take a screenshot of this. Okay, so we are seeking a specific volume of 0.1741. 0 V equal to 0.1741 and P equal to 1000 kilopascal. So over here we have V and 1741, so it should be somewhere between these 2 points, no? I'm just highlighting the U as well, so let me just write it like this. So we have V, we have U, V is 0.17389, 0.18477, 0.1741. Corresponding to this, the U is 1490.5, over here 1528.6, and over here we will have U2, which is what we need to find out. So we can write down U2 minus 1490.5 is equal to 0.1741 minus 0.17389 divided by 1528.6 minus 1490.5 divided by 0.18477 minus 0.17389. So this gives us what? Okay, let me turn on my trusty calculator. I call it trusty calculator because it's literally been running since 2007 and I was a first year student. It never gave up. It's crazy reliability if you ask me. No one has to be as reliable as these items. Casio 0.18477 minus 0.17389 times 1528.6 minus 1490.8.5 plus 1490.5. The value I'm able to obtain is, who knows it is correct. It is 1491.23. Or have I made a mistake? I might have made a typing mistake. Has anyone done this interpolation?
Yes, sir. It's coming out to be 1491.23.
Okay. 1491.23 kilojoule per kg. No problem. Make sure you do not do any calculation mistakes in this. Just try to ensure that. Anyway, this minus this would not cause a big deal. Actually, see, every table, everything has a certain offset to it. We never know what the offset is. Because why do we not know whether this value should match or not? Every table can have an offset. You can select any point to be 0. So just to be on the safer side, we should also fetch what the internal energy for the first state should be. Because we are doing it properly, let's just do it. Next problem onwards, we won't do it all the way. So for the first data, 0 degrees Celsius, let me just take a screenshot. And I want to comprehensively show you that maybe it is the offset that is creating the issue. So the first state is 0 degrees Celsius, and these are the internal energies, specific internal energies. So the what is the U1? It's going to be 179.69 plus 0.6 multiplied by 1138.3. Okay, because this is UFG. So what do we have? 179.69 plus 0.6 times 1138.3, and I get 862.67 kilojoule per kg. See, you see the offset? So just to prove that point further, let us do U2 minus U1 from tables. U2 minus U1 from tables. This is gonna be 1491.23. And if I multiply, so this is 628.56. So Q12 will be mass times U2 minus U1. So what was the mass? 1.148. That comes
Yes,
up
sir.
to 721.58 kilojoules. Okay, so what do you say? Not
Related.
bad. So do not be confused if the table and if the book show you different absolute values of U, because there is nothing known as absolute value of U. It all depends on where you choose the offset for U. Is that clear to everyone?
Yes, sir.
So let me just stop recording. Stop recording.